Let's compare convergence of a sequence with the convergence of a series. Unfortunately, a lot of students mix them up. And we're going to do that using the following sequence. So we have a sequence of numbers a sub n equal to 2 multiplied by 1 plus 3 divided by n to the power n. First, I'm going to show you how on the calculator you can see if this sequence actually converges or diverges. So we're going to open the Desmos calculator and we are going to type this equation in the calculator. So when you have a powerful tool like Desmos, you should use it. Okay? Now, convergence of a sequence means that it's going to have a limit that's a number. How do I know that? Well, I will need to increase the values of n and see if it's going to just grow unboundedly large, possibly because this is a positive sequence, so it's not going to alternate signs. Or maybe it'll start approaching some numbers. So I'm going to try a of 10, okay? Then 100, then 1,000, 10,000, and so on. Now, at this point, once I start adding more and more zeros, it does look like it's getting closer and closer to something like 40.17, at least at a million, I think that's what it is. If I add another zero, again, it's 40.17, and it's not really changing that much, especially in the first few decimal places. Let's try again. Again, it's the same number. So at this point, I think the sequence is going to converge. So at least I know that that's going to happen. Okay. Now, to figure out the limit, I have to know more. There is a famous limit in calculus, and it is proven by using exponential and natural log. But the limit looks like this: 1 plus a divided by n to the power n. That thing is going to converge to e to the power a. Okay, now I do have it on the formula sheet here. So this sequence, the second line right here, that's e to the power a. Now let's see if that works in this case. So for me, I have 1 plus 3 over n to the power n. So that should be e cubed. But I also have that 2 here, so that will just be preserved because that's a constant multiple. Let's see if we can multiply 2 times e cubed and see if that's it. And it's exactly what it is. So that sequence converges and the limit is 2e cubed. Now, what does it mean for a series to converge? Here we need to use possibly one of those tests. What's the difficulty? Why is it so much more difficult to figure out when the series converges as opposed to when the sequence converges? Convergence of a series is also convergence of a sequence. It's just it's not this particular sequence. It's the sequence of partial sums. So what are these partial sums? Well, the first one is just a of 1. Okay, the next one is a of 1 plus a of 2. So you're not looking at the terms, the a's, but you're looking at their sums. The next one is a of 1 plus a of 2 plus a of 3. And you can continue doing that, because unfortunately with the Desmos calculator, you can't really, this particular one, you can't really figure out whether it's going to convert to some limit because you can't plug in stuff like 10, 100 like you do with sequences, but at least you can tell what's happening. So one thing that you should note is that if the A numbers, if they don't approach 0, there is no way for this thing to converge, okay? Because if you keep adding numbers and the numbers are either growing or staying at the same value, but they're not going down, there's no way for infinitely many numbers to add up to some number. So if these A numbers are not going to 0, that's not going to happen. The series is going to diverge. And the very first thing you immediately ask yourself, what about divergence test? So what does divergence test say? It's a very powerful test, but it can only be used to prove convergence or divergence of a series. And actually, to only prove divergence of a series. It's not going to prove convergence ever. It's just going to be inconclusive. So what does divergence test say? Well, let's just say you have the general series, right? And it says, if you take the limit of the sequence of the numbers an, so drop the sum and instead substitute the limit, if this limit is anything other than 0, the corresponding series automatically diverges. But if the limit is 0, the divergence test does not tell you anything. So it's inconclusive, and it doesn't mean the series is going to converge. It absolutely doesn't. Otherwise, if it was that simple, then we wouldn't need any of the other tests, and we have like 100 more tests here. But the divergence test should be tried first. So the series diverges. Why? Because our limit of an, which we did in part A, is 2e cubed. And obviously that is not zero. So there is no way for these sums to converge anywhere. So we're just going to say that that's divergence test. And the sum is, well, if there is no sum, we're just going to enter G and E, does not exist. And let's see if that works. All right, it worked.